Good morning, everyone. Welcome to Guru Brahma classes for JEE and NEET. Today's topic is chemical equilibrium, and in this session, we are learning the concepts regarding chemical equilibrium. Topic chemical equilibrium. So, let us see that. Chemical equilibrium or equilibrium in chemical process. Equilibrium in chemical process. So, in a chemical reaction, let us take a chemical reaction. A plus B gives rise to C plus D. So, A plus B giving rise to C plus D. If you write a single-headed arrow, it represents that it is irreversible reaction. What is that reaction? Irreversible reaction. In an irreversible reaction, chemical equilibrium is not possible. Why it is not possible? For a reaction to attain chemical equilibrium, there should be both forward reaction and backward reaction. In an irreversible reaction, we have only forward reaction. So, chemical equilibrium cannot be obtained in an irreversible reaction. It's not possible. So here, when you are seeing this reaction, you will find that double-headed arrow. See, it has both the forward direction arrow, okay, forward direction C plus D, and backward direction. So this reaction proceeds in both forward direction as well as backward direction. It has forward reaction and backward reaction also. Such reactions are called as what we have studied, that it is reversible reactions. In a reversible reaction, at a particular after a particular time, no doubt about it, a reversible reaction will attain equilibrium. Okay, a reversible reaction will attain equilibrium after a certain time. So, chemical equilibrium can be obtained in a chemical reaction. Which type of chemical reaction? Reversible chemical reaction. So, chemical equilibrium can be obtained in a reversible chemical reaction. So, that equilibrium in a chemical process we are speaking about. Okay. So, here what are the reactants? What are reactants? A and B are reactants. A and B are reactants. Right? So, let us take a container. In this water present, A and B are present. Water present, A, B, A, B. So, A and B are what? Reactants. A and B are reactants. So, initially in this reaction mixture, there are only A and B. Only A and B. Right? There is no C, D formed because the reaction hasn't started. Just reactants are there. And the number of reactants are more. Okay. The number of reactants are more. That means reactants. What are reactants here? A and B. Initially, the number of reactant molecules, A and B molecules, are more. As the number of reactant molecules are more number of reactant molecules combine. Combine means they react. So, initially, more number of reactant molecules react with each other. Okay. When they react, there will be some change in the concentration of the reactants. There will be some change in the concentration of the reactants. Let us take rate. What is meant by rate of a reaction? Let us see this. What is that? Rate of a reaction. Rate of a reaction is generally represented by a small r. It's represented by small r. It is with respect to reactants, let us say, change in concentration of reactants in unit time. Change in the concentration of the reactants by time. Okay. Initially there will be much change in the concentration of the reactant. Why there is much change in the concentration of the reactant? Because more number of A and more number of B are present. More number of A and more number of B are present initially. So more number of A and B react. When more number of A and B react, more change will be observed in the reactants. More change will be observed in the concentration of the reactants. For example, in 10 seconds, rate R with respect to reactants. Reactant A, if I take rate with respect to reactant A. So what is that? Change in the concentration of the reactant. Change means I write delta. Change in the concentration of reactant with respect to A. Change in the concentration. Concentration is represented whenever some reactant or product is represented in the form of square brackets. We have to remember that that is the concentration of the reactant or product by change in the time. Okay, so this is called as rate with respect to A. So this change will be more initially. What is that? This change will be more initially. Okay. See, for example, here what is forward reaction in this A plus B converting into C plus D is called as a forward reaction. Okay, let me write it as F. Okay, what is that? F. F means here forward reaction. So here you are finding forward reaction. Right? So A plus B converting into C plus D is forward reaction, and C plus D converting into, okay, A plus B, arrow you can see, backward reaction. Backward reaction, right? So first in the reacting vessel, what are present? Only A and B are present, and more number of A and B are there. When more number of A and B are there, more A, B react. When more A and B react, there will be more change in their concentration. If there is more change in their concentration, then the rate will be more. See here, when you are drawing graph, rate is taken on y-axis and time is taken on x-axis. Okay, how is the rate of the how is the rate? Initially very high. You can see this dot. Rate is very high. As the time proceeds, see, at the time 0, that means just it has started, its rate is very high. As the time proceeds, the rate of the forward reaction decreases. Why the rate of forward reaction is decreasing? Because as the time proceeds, the number of reactant molecules decreases. When the number of molecules decreases, then the change in the number of reactant molecules or change in the concentration of the reactants decreases. So as the time proceeds, that means as the reaction proceeds, the number of reactant molecules or the amount of reactant, the amount of the reactants decreases. Okay. So as the number of molecules decreases, so the reactants reacting decreases. Change in the concentration of reactants decreases with time. If the change in the concentration of reactants decreases, automatically rate decreases. That is what it is shown in this graph, you see. As the time is proceeding, as the reaction is proceeding, the rate is decreasing. Time increasing, rate decreasing. Rate decreasing. Time increasing, rate decreasing. Why rate is decreasing? Because as the time proceeds, as the reaction proceeds, the number of reactant molecules decreases. So the reactant molecules reacting decreases. So the concentration of the reactants also decreases. Okay. So the rate automatically decreases. Okay. So initially there are only A and B in the container. Now as the reaction happens, what happens? As the reaction proceeds, A and B decreases. What happens? A and B decreases and C and D starts increasing, right? A and B. See, actually A, B, A, B, A, B, A, B. In this way, we have reactant molecules. As the time is proceeding, what happens? A, B are converting into C, D. A, B are converting into what? C, D. That means reactant molecules are decreasing and the product molecules are slowly increasing. Product molecules are slowly increasing. Okay. So initially there are no product molecules. So what is backward reaction? Backward reaction means CD converting into AB. That means products are converting into again reactants. Okay. Backward reaction. So I can also express this rate of the reaction with respect to products also. With respect to products. So rate with respect to product. If I say one product C, then I can write a change in the concentration of C by change in the time. So rate is discussed in this way. Change in what? The concentration. Change in what? The concentration. Right? So as the time is proceeding, as the reaction time is proceeding, C molecules and D molecules are increasing. Initially we don't have any C and D products. As the time is proceeding, what happens? C and D are increasing. C and D are increasing. As C and D are increasing, A and B are decreasing because A and B are converting into C and D. A and B are converting into C and D. Okay. So after the formation of a particular amount of C and D, again the C and D will convert into A and B. Already we have studied that A and B reactants converting into products is called as forward reaction. Products converting into reactants is called as backward reaction. So when does this backward reaction occurs? When a sufficient number of product molecules are formed, these products now behave as reactants. They react with each other and convert into A and B. Here products are C and D. This now C and D are behaving as reactants, and they are reacting with each other and converting into A and B. So in the backward reaction, C and D becomes reactants, A and B becomes products. In the forward reaction, A and B are reactants and C and D are products. Okay. So here there is change in the concentration of reactants with the time and change in the concentration of the products with the time. This change in the concentration of reactants is called as rate. Change in the concentration of the products is called as again rate. Okay, when A and B are converting into C and D, there is some change in the concentration of the reactants, and that is called as a rate of forward reaction. What is that? Rate of forward reaction. What is meant by rate of forward reaction here? The change in the concentration of the reactants with the time is called as rate of forward reaction. I can write here what is rate of forward reaction? Change in concentration of reactants with time. Then what is rate of backward reaction? Rate of backward reaction. Rate of backward reaction. What I can say, what is rate of backward reaction? Change in concentration of products with time. When this rate of forward reaction is equal to rate of backward reaction, when this rate of forward reaction is equal to rate of backward reaction, then I can say that it is a chemical equilibrium for a chemical reaction. What is that called as? Chemical equilibrium. How can we define chemical equilibrium? How can we say that a chemical reaction is attaining chemical equilibrium? The one way of saying it is when the rate of forward reaction is equal to rate of backward reaction, then that is called as a chemical equilibrium. Okay, so from the graph we can observe that rate of forward reaction, as the time is increasing, it decreases, and rate of backward reaction, as the time is increasing, it increases. Okay. Why rate of backward reaction is increasing? As the time is increasing, the number of products are increasing. As the number of products are increasing, these reaction of products increases, because more the number of products are reacting, then that will be more the rate of backward reaction. More the rate of backward reaction. So at this point, you see, at this point, the rate of forward reaction is equal to rate of backward reaction. Hereafter, from here to here, the rate of forward reaction is equal to backward reaction, and from here to here, I can mention that it is a chemical equilibrium. Chemical equilibrium. Understood? Right? So let us see what the points are given here. In the beginning, the rate of forward reaction is more since the concentration of the reactants is high. As the time proceeds, it decreases due to decrease in the concentration of reactants. So initially we have more the rate of forward reaction. As the time proceeds, its rate of forward reaction decreases due to decrease in the concentration of the reactants. In the beginning, the rate of backward reaction is 0 because there are no products. Because the concentration of products is 0. As the time proceeds, it increases due to increase in the concentration of the products. As the time is increasing, what happens? The concentration of products increases, so the change in the concentration of the products increases, so the rate of backward reaction increases. Initially it is 0. The state or stage at which the rate of forward reaction is equal to the rate of backward reaction or reverse reaction is known as reversible reaction, and this condition is called as what? Equilibrium stage or state. What is equilibrium? Chemical equilibrium. It is the state or stage where the rate of forward reaction is equal to rate of backward reaction. So equilibrium is established in a only reversible, not possible in irreversible reaction. It is possible only in reversible reaction, and it happens only in closed vessel. When it is opened, generally if the products are gaseous or reactants are gaseous, they escape. When they escape, the possibility of reversible reaction will be very much less. So it occurs generally in closed vessel, and it occurs at a constant temperature. Okay, that is about the basic thing regarding chemical equilibrium. Next, equilibrium in a chemical process is dynamic. It is dynamic. Okay, so when a reversible reaction, at equilibrium, both the forward reaction and reverse reaction continue to take place with equal rates. Hence, equilibrium is dynamic in nature. So, what is the meaning of dynamic here? Means at equilibrium, the reversible reaction. At equilibrium, the reversible reaction appears to be stopped. How does it appear? It appears to be stopped. Actually, it does not stop. Why it is appearing to be stopped? It is appearing to be stopped because its physical properties like color, state, its physical properties like concentration, they remain constant. As they are remaining constant, at equilibrium, the reaction appears to be stopped, but actually the reaction does not stop. Both forward reaction and backward reaction continues to take place with equal rates. So what is dynamic here represents? The dynamic here represents that at equilibrium, both the forward reaction and backward reaction continues to take place. But reaction appears to be stopped, but it does not stop. As both the forward reaction and backward reaction continues to take place. That is the reason why it is called as a dynamic. Chemical equilibrium is dynamic in nature because both forward reaction and backward reaction continues to take place with equal rate. Okay, that's the meaning of dynamic. That but it does not stop. Okay. Both forward reaction and backward reaction takes place, continues to take place with equal rates. That's called as a dynamic in nature. This dynamic nature of chemical equilibrium can be obtained, can be demonstrated in the synthesis of ammonia by Haber process. So in the synthesis of ammonia by Haber process, they have conducted an experiment and found that the chemical equilibrium is dynamic in nature. So let us see here, in a container, what is given, what is taken, N2 plus 3H2 gives rise to 2NH3. This equilibrium reaction is taken. This equilibrium reaction is taken means, so this reaction is in equilibrium. This reaction is in equilibrium. Equilibrium, already we have studied that the rate of forward reaction is equal to rate of backward reaction. That means in the container what are present? N2. That means N triple bond N, 3, H single bond H, 2, N, H3. So these are present. Okay, these are present in a container. Along with this, another equilibrium state reaction is also taken. What is that? N2 plus 3D2. What is D? D is deuterium. Okay, isotope of hydrogen. Isotope of hydrogen. Hydrogen has 3 isotopes. What are those? What are the isotopes of hydrogen? One is hydrogen 1,1, another hydrogen 1,2, another hydrogen 1,3. There are 3 isotopes of hydrogen. One is called as this is called as protium. This can also be called as protium. H12 is called as deuterium. H13 is called as tritium. So this is what deuterium. H12, atomic number 1 and atomic mass 2. That's called as what? Deuterium, isotope of hydrogen. This is also hydrogen, but isotope. It is a isotope of hydrogen, heavier isotope. So in the same container where N2 plus 3H2 gives rise to 2NH3 is present, in the same container we have taken N2 plus 3D2 gives rise to 2ND3. Okay, this also, this reaction, second reaction, this is, let us take this as first reaction. What is that? This is first reaction, this is a second reaction. 2 reactions which are in equilibrium are taken in a container, in a closed container. Okay, so that means N triple bond here, D single bond D. Okay, 2 N D. So these are present. These are present in a container. Okay, and left. First reaction is in equilibrium and second reaction is also in equilibrium. These are all these 2 reactions which are in equilibrium are present in a container, closed container, and left. After some time, when it is observed, if the reaction does not occur at equilibrium, and if the reactions does not occur at equilibrium, for example, let us take, what should be present in the container? In the container, there should be N2, H2, NH3. This is what, when we are speaking when the reaction has stopped. If the reaction has stopped, there should be who? N2, H2, NH3. There should be N2, D2 and ND3. Only these: nitrogen, hydrogen, NH3, ND3, T2 must be present in the container. But what are present in the container? After leaving the container for some time, it is found that along with NH3, there is a different one called as NH2D is present, NHD2 is present, right? There is HD is present. Where did they come from? Along with NH3, ND3, H2, D2, these different composition containing compounds are also observed. Where did they come from? If the reaction has stopped at equilibrium, the presence of this NH2D, ND2, HD. Such other species in the container shows that the reaction has not stopped. The reaction is continuing. Which reaction? Both forward reaction as backward reaction are continuing to take place. From this, they have observed that at equilibrium position, the reaction does not get stopped. Both forward reaction and backward reaction continues to take place. Okay. Let us see here, if N2 and 3H2 has to combine and form NH3, first of all, nitrogen, what should happen? Nitrogen bond must be broken and convert into nitrogen atoms. Hydrogen bond must be broken and convert into hydrogen atoms, and nitrogen and hydrogen has to combine and form NH3. So this is what happens. First of all, the molecule must convert into atom, the molecule must convert into atom, then these atoms must combine to form another new molecule, NH3. This is the process. Here also, nitrogen atoms, deuterium atoms, and ND. So when both reaction 1 and reaction 2 are present, there are species here. What species are present? Nitrogen atoms are present, hydrogen atoms are present, deuterium atoms are present. If the reaction has stopped, only a different species cannot be formed. Now different species are also formed. What this nitrogen is combining with the deuterium, like NHHD can be formed. NHD is formed. Okay, and this hydrogen species are there, deuterium species are, they can also combine. HD is found to be seen. Understood? So why different species apart from the reaction mixture we are finding? This represents that the reaction has not stopped in a chemical equilibrium. The reaction continues to take place. So from this observation, from this experiment, it is found that at chemical equilibrium, the reaction does not stop. That is how dynamic nature of chemical equilibrium has been obtained, discussed or described. Right? So use of isotope deuterium in the formation of ammonium clearly indicates that chemical reactions reach a state of dynamic equilibrium in which rate of forward and reverse reaction are equal and there is no net change in the composition. Okay. So let us see. On the y-axis, what is taken? Molar concentration. Concentration is taken, whether it is reactant or product. See, here it is ammonia. Ammonia is a product. Ammonia concentration is 0 because at time t is equal to 0, there is only hydrogen and nitrogen. There is only hydrogen and nitrogen. There is no ammonia. That is the reason why its concentration is 0. As the time is increasing, the concentration of hydrogen, what happens? As the time is increasing, the concentration of hydrogen decreases. Why hydrogen is taken more? It is 3H2 and nitrogen is only N2. So 3 moles of hydrogen and here only 1 mole of nitrogen. That's the reason why less. Okay, here it is more. As the time proceeds, what happens? Hydrogen, nitrogen combines. That means the concentration of hydrogen as well as nitrogen also decreases. See, nitrogen concentration decreasing, hydrogen concentration is also decreasing. And nitrogen, hydrogen combines to form what? Ammonia. Its concentration has increased. See, its concentration from 0 to it has been increased. So as the time proceeds, hydrogen concentration decreases because it is participating in the reaction. Nitrogen concentration decreases because it is also participating in the reaction. Ammonia concentration increases because nitrogen, hydrogen combines to form ammonia. Right? So you are finding there is some decrease in hydrogen concentration, nitrogen, increase in concentration of ammonia, but after a particular time, their concentrations are found to be constant. From here it is constant, you see, here it is constant, here it is constant. What is this constant concentrations of hydrogen, nitrogen, ammonia represents? This represents from here onwards, it represents that it is it has attained chemical equilibrium. It has attained what? Chemical equilibrium. That means at chemical equilibrium, the concentration of the reactants and concentration of the products remain same. It's not equal. Are they equal? No, they are not equal. They are remaining constant. So at chemical equilibrium, we have to remember that the concentration of reactants and concentration of products remain same. What is that? Remain same. They does not change. They remain same. Remaining same does not mean that they are equal. They may be equal, but there is only one chance. But there are infinite number of chances. There are numerous chances where their concentrations cannot be equal. Their concentrations can be equal, will be only one chance. But there are numerous chances where their concentrations cannot be equal. But their concentration, what you need to remember is their concentration must be remain same. Their concentrations does not change at chemical equilibrium. Whose concentration? Hydrogen concentration, that is reactant concentration and product concentration. So at chemical equilibrium, reactant concentration and product concentration remain same. Okay. Next, let us see characteristics of chemical equilibrium. So at chemical equilibrium, rate of forward reaction is equal to rate of backward reaction. Already we have seen. It is dynamic in nature. That means at chemical equilibrium, the reaction does not stop. Both forward reaction and backward reaction continues to take place with equal rate. The properties such as pressure, concentration, density, color remain unchanged with time. So properties like pressure, concentration, density, okay, color, they are remaining constant. Unchanged means they are remaining constant with the time. So catalyst does not alter the state of equilibrium. It only speeds up the attainment of equilibrium. So when you use a catalyst means already we have studied the definition of catalyst. Catalyst is the substance which participates in the reaction, which increases the rate of the reaction but does not undergo any change, any net change. Catalyst substance which increases rate of reaction. What is that? Which increases rate of reaction. Catalyst participates in reaction but does not undergo any net change. That means Before the reaction, how the catalyst is present, how much the catalyst is present. After the reaction also, catalyst will be present in the same state and the same amount. That is the meaning of does not undergo any net change. There will be no net change in that substance. So when you use a catalyst, equilibrium can be obtained very early because it is increasing the rate of the reaction. As it is increasing the rate of the reaction, equilibrium can be obtained earlier, faster. For example, there is a reaction, particular reaction, in which the equilibrium is obtained after some 10 minutes. If you use catalyst, it will be obtained within 5 minutes. That is what the catalyst does. The catalyst increases the rate of the reaction. At equilibrium, delta G is equal to 0. What is delta G? Change in Gibbs energy, change in free energy. Its change will be equal to 0. Okay, these are the conditions which we need to remember. Chemical equilibrium can be established from either side of the reversible reaction. For example, let us take in a container, you have taken N2 reacting with H2. Initially, what did we take? N2 and 3H2. So NH3. So initially, by taking N2 and 3H2, we have obtained chemical equilibrium. This can also be obtained by taking ammonia. If you take ammonia, okay, it is dissociating into N2 plus 3H2. So here similar equilibrium. Ammonia is in equilibrium with nitrogen and hydrogen. In this also ammonia is in equilibrium with nitrogen and hydrogen. This equilibrium is obtained by taking N2 and 3H2 and nitrogen and hydrogen. In this container, equilibrium is obtained by taking ammonia. That is what they say. Equilibrium can be obtained from reactant side or from the product side. That means by taking reactants you can obtain chemical equilibrium, or by taking products you can obtain chemical equilibrium. Okay. Then the concentration of reactants or the products remains unchanged with time. That is what it is seen here, shown here. You see, in the first graph, what do you see? What you find? Reactants. This is reactant. This is R0, means R0 is initial. This is y-axis. On y-axis, what is taken? Concentration. R0 not represents that initially at 0 time. 0 time. As the time proceeds, what happens? Reactant concentration decreases, but after some time the concentration of the reactant is remaining constant, product is also remaining constant. Initially at 0 time there is no product, 0. As the time proceeds, product concentration increases. So after this particular time, reactant concentration and product concentration is remaining constant. So this shows that it is this has obtained chemical equilibrium. Chemical equilibrium. Here also you can see there is one chance, I said before, only one chance where reactant concentration is equal, reactant concentration and product concentrations are equal. Here they are equal, and they are also constant. They are also constant. You see, constant. They are also constant here. As they are constant, we say that again this is also a state of chemical equilibrium. Here also they are remaining constant. You see, constant product concentration, reactant concentration remaining constant. So this is the state of chemical. What is that? Chemical equilibrium. Okay. So at chemical equilibrium, the concentration of the both reactants and products remain constant. What we need to remember is remain constant, right? Next, coming to the types of chemical equilibrium based on the state of the reactants and products. chemical equilibrium can be homogeneous or heterogeneous. Homogeneous equilibrium means if the reactants and products are in the same phase, same state, then the equilibrium is said to be homogeneous equilibrium. See here, gas H2 plus I2 gives 2HI, all are in gaseous state. N2 plus 3H2 gives 2NH3, all are in gaseous state. 2SO2 plus O2 gives rise to 2SO3, sulfur trioxide, all are in gaseous state. So acetic acid, what is this? Acetic acid, ethyl alcohol, okay, ethyl acetate, all are in which state? Liquid, all are present in the liquid state. Okay. So as all are present in the liquid state, this is again homogeneous. Homo means same. If all the reactants and products are present in the same state, such equilibrium is called as homogeneous equilibrium. Like Fe plus 3, ferric ion, thiocyanate, okay, ferric thiocyanate, all are present in aqueous state, aqueous. So in all these reactions, you are finding the reactants and products are in the same state. That is the reason why they are called as, their equilibriums are called as what? Homogeneous equilibrium. Coming to heterogeneous equilibrium. So heterogeneous, different. If the reactants and products are not in the same phase, then the equilibrium is called as heterogeneous equilibrium. See here, calcium carbonate solid, gas. All are not in the same state. Here you can find solid, gas. Here solid, gas. So here you find a solid, aqueous solution, liquid. So when reactants and products are not in the same state, then such equilibrium is called as a heterogeneous equilibrium. Right? Hope so you understood very well. That is all with the concept of chemical equilibrium. Let us wind this session and we shall meet with the next topic in the next class. Thanks for watching.